We're now going to be looking at sections 23.7 and 23.8. We're going to be looking at reflection and refraction. What's the difference between the two, and total internal reflection. So when we transfer from one medium to the next, light has this funny way of changing speed. And so how do we gauge that? What do we do? The index of refraction is going to be our way to do that. It's basically a ratio of the speed of light in a vacuum to the speed v in a material. So the incident, reflected, and refracted rays and the normal to the interface all lie in a single plane called the plane of incidence. Angles of incidence, reflection, and refraction are always measured from the normal to the interface. The law of reflection states that the angle of incidence and reflection are going to be equal. And again, we'll see that this is just the summary. The law of refraction is going to be a sine relationship with these angles here. And again, we'll get to that in just a second. So when a ray travels within a material of greater index of refraction NA towards an interface with one of a smaller index, the total internal reflection occurs when the angle of incidence exceeds a critical value given by this. In other words, incident, reflected, and refracted rays. So you've got the reflected ray, you've got the ray coming in here. This is what's being reflected because this is the border between the two substances. This is what's being refracted. Now, reflected, of course, means it's just simply being bounced off. Refracted means that it's continuing its forward motion, its angle towards this normal of the interface in between the two. Its angle here with that normal has changed. And so this is going from something that has a smaller index to something that has a greater index. So this is what you are seeing here, that the angle of reflection and the angle of incidence here is going to be the same. And the sine of A and B, that ratio here is going to be equal to the ratio of the index of refraction here divided by the index of refraction here. So those are going to be the major takeaways from these two sections. So again, we've got our incident rays, we've got our reflected rays, and we've got our refracted. So this is going to be the interface here. We're seeing the waves in outside air, and then as it strikes glass, this is going to be the how things change. So as we're going through here, you can see two different types of reflections here. You've got, let's see if this is spelled out. We're going to be paying most of our attention to smooth interfaces where the reflected ray travels at a definite angle. This is going to be called specular reflection. Scattered reflection from a rough surface is going to be called diffuse reflection. This distinction is illustrated here in this particular picture. So when your bathroom mirror fogs up from the shower, the otherwise specular reflection becomes diffuse, simply because you got water on the surface. It's not going to be smooth anymore, and so you're going to end up with this junk. So again, your index of refraction is going to be the ratio of the speed of light in a vacuum divided by the speed of light in some other medium. Light always travels more slowly in a material than in a vacuum. So N for any material is always going to be greater than 1. So a vacuum is going to be defined as 1 by definition. So here we're going to be taking a look at incident, reflected, and refracted rays and the normal to the surface, and they all lie here in the same plane. So what we're finding here is that when we look at the normal here, the incident ray and the reflected ray, those angles from the normal are going to be equal to each other. We're also going to see that the incident ray coming in here to the substance B is going to be refracted or changed in some way, but it's still going to continue its forward motion. If it's monochromatic light and it crosses the interface between the two substances, the angles are related to the indices for refraction in this method. This is going to be referred to as the law of reflection. This relationship is going to be equal for all wavelengths for any pair of substances. When the light ray crosses the interface between two substances having different indices of refraction, the trajectory of the ray changes abruptly at the interface. The precise manner in which the direction of the ray changes is determined by the mathematical relationship known as Snell's law. And that's what this is going to be. That's what you saw up here. So this is going to be referred to as Snell's law. The bending of the light ray is always such that the angle on the side with the higher index of refraction is the smaller one. So in other words, if you're going here with this particular refraction, you're going to be seeing here that this refraction is going to end up with a smaller angle than what you had over here. The angles are with respect to normal to the interface, of course. And then if the ray intersects the interface at a right angle, then there is no bending. So a ray entering a material of larger index of refraction bends towards the normal. A ray oriented perpendicular to the surface, in other words, it's coming here, does not bend regardless of the materials. So in other words, as it goes in, it might be reflected back, or if it's refracted, it just goes straight on. If it enters a material of smaller index, then what you are seeing here is that this angle is going to be greater than this particular angle. So these are some pictures that you might want to take with you as you're working this particular section. So the path of a refracted ray is reversible. This is the same from either direction. In other words, if you've got a ray that's coming in here and strikes the surface where this is going to be, and this index is going to be greater than this, whether the ray is going in this direction or whether the ray is going in this direction, this pathway is always going to be the same. It's just a question of which way the photons are going. Obviously, the reflection here is going to occur in this part of the medium as opposed to over here if the ray is coming from this direction. Same is going to be true here for this reflected ray. If it's bouncing this way, you will see some refraction here, but you will see the reflection going this way as opposed to over here where you will see it going back this way, but you're seeing the same pattern there. You can see the index of refraction for yellow sodium light in all of these different types of materials. So that's a very basic description here of what goes on as far as light in its interaction with different surfaces. So there's several other problems here that you can go through. I encourage you to do that. Now, let's take a look at 23.8. Total internal reflection. So if we take a look at this particular figure here, we've got several rays diverging from a point. So all these rays, 1, 2, 3, 4, they're all coming from this particular point in a material A with index of refraction N sub A. The rays strike the surface of the second material. And so from Snell's law, you can see what all of these angles end up being. Obviously, if it's coming in like this, and it just goes through in the same pathway, if it's at 90 degrees, here you can kind of see a little bit more of a bend. If you have if it goes through and this ends up being greater, or this ends up being greater than that, That's where you can see more of a bend here. What you're also seeing here is that at the critical angle of incidence, that you're seeing the angle of refraction ends up being 90 degrees. And what you're also seeing here is that any angle that is greater than the critical angle to the normal, which as measured here, that it ends up getting total internal reflection. In other words, it's not penetrating over here. The light is being bent to the point where it's just being bent backwards back into this particular medium. This only occurs if this, again, is smaller than this. In other words, your index here is going to be smaller than what you're running into here. But again, that is something to remember here in terms of your indices of refraction, how they relate to each other. So the critical angle for total internal reflection ends up being this. So you got several different applications there of that. So that is something for this particular situation to remember from Snell's law.